Numbers, numbers everywhere. Now, as you study mathematics, you probably spent some time looking at the components of mathematics. What I'm going to talk about today a little bit is I'm going to talk to you about properties or a specific property of very large data sets. Now, let's talk about numbers a little bit. Now, you're used to probably using numbers such as integers, which are whole numbers, and real numbers, which have decimals, and there's probably a whole bunch of other ones that you use by now. So you're at least getting used to, in the world of mathematics, of looking at numbers and seeing that specific numbers have different properties to them. So when you perform things in numbers, if you're doing anything like with mathematical theory or anything that has to do with even simple algebra, you're starting to see that numbers have specific properties, such as primes, non-primes, and things of that nature, just to give you a couple simple examples. Now, to take that example a little further, you have sets of numbers that have specific properties too. And you've seen that when you've worked with statistics, when you would have, a population, or you would have a sample of a population. And then you would see that those sets of numbers, or a series of them, have properties as well. Now, the most simple properties that you've seen with sets of numbers are things such as an arithmetic mean, mode, median, and you've probably done things such as standard deviations and variances. And from there, you could do things such as some simple predictive modeling, such as z-scoring, to look at where a specific value would be on a curve. Okay, so I'm trying to sell you on numbers having different properties, and I'm trying to make you think about things you already know about how specific numbers have properties and how sets of numbers have properties. Okay, good. So let's move on. What I'm trying to get across to you for this video here, what I'm trying to talk about is one of the properties of large data sets is called the law of large numbers. Say that 10 times quick. The law of large numbers. So what I'm going to do over the next few minutes is, rather than bore you with a bunch of gobbledygook math, which I'm going to do anyway, but maybe not today, I'm going to try to sell you on the concept of what the law of large numbers is. Now, the law of large numbers is used in predictive mathematics. Now, we have looked at, or you may have looked at, the two different kinds of math, descriptive math and predictive math. Now, remember, what descriptive math does is it takes samples and it tells us about them, right? A very simple example of descriptive math is taking a mean of something. You guys already know how to do that. When you were in grammar school and you learned how to get a mean of something or an average of something, you were doing descriptive math. Now, as you started getting, into your middle school and high school career, your descriptive math hopefully got a little bit more complex. Statistics, really, when you're doing statistics at the high school or at the college level, that's really a way of doing descriptive math. You're describing things, right? You're describing large sets of data, their variances, their standard deviations, their, anything that has to do with all of them as a whole is describing them, or descriptive math. Now, on the other side of that, we have predictive math. Now, predictive math is basically the following. It looks at what the predictive math tells us, and it allows us to make predictions. What does that mean in English? Well, that means in English, if we can model anything in the past, we could take that model and make predictions of what is going to happen in the future. Now, Einstein said something that actually rang very well with me, saying that the future is just a past event that has not occurred yet. Think about that. The future is just a past event that has not occurred yet. So that is exactly how predictive math works. What predictive math does is it basically says, okay, if this was in the future, I could take the predictive models that I've built and I can expand them up to the present day, which is basically in some ways predicting the future. Now, it doesn't work quite that easily. You hear people, with algorithms for lottery tickets or counting cards if you're doing anything in Las Vegas. Believe me, that does not really work. So when I'm talking about prediction, I'm talking about looking at the past models that you've done for predictive math and then building predictions based on them. So the first law, or one of the biggest laws that I'm going to introduce you to today, is called the law of large numbers, which I've previously stated. Now, the law of large numbers just tells us that if we know the mean of a population, as we approach the mean, or as the mean approaches infinity, that all of our values and our future values are going to tend to gravitate towards the mean. Now, that's going to sound a little bit mathematicky on you, and that's okay for now, because later we're going to go over this in a little bit more depth. Right now, I'm just trying to sell you on the concept of that. So let me give you a simple example of that. Let's take, for example, if I had the mean age of a population. Let's just say the population of all students at this college, at Triton College, let's just say the mean age was 20 years old. Let's just use a round number. I'm sure it's different than that, but just work with me on this. So anyway, if we know that the population mean is 20, and as we take our samples, the first student, was Bob, and we say, Bob, how old are you? He says, I'm 19. Then we ask the second student, Cadence, how old are you? And she says, I'm 17. And then we have the third student, Rue. How old are you, Rue? And Rue says she's 21. So think about what I'm doing here. What I'm doing is I'm slowly leading you through at least the concept of the law of large numbers. So what I can do is every time I take a sample of that age, I can add that and get an average, right? I could say, well, when I ask Bob how old he is, Bob says, I'm X years old. So what I can do is I can get the mean. I could say, well, the sample mean now is really just Bob, right? But as I ask Cadence and Rue what their ages are, I can take the sum of their ages and divide it by n, which is the number, and I could get the mean of those three samples or students. Okay, now I have not told you anything you probably don't know yet. Here is where it gets cool. So as we get closer and closer to our population, there are a few things that we can predict, or there are a few laws that apply to our math. And one is called the law of large numbers. Again, as I've mentioned that before, the law of large numbers just means that running mean that I'm telling you, like when I have 3 students and 4 students and 5 students, one of the things that the law of large numbers tells us is our running mean will fluctuate around the population mean. And as our samples approach our population, there's one thing that law predicts with 100% certainty. There's a 100% chance that our running mean, as we sample each individual observation, eventually it will converge to our mean for our population. So with that in mind, there's a lot of really cool things that you can do, or the law of large numbers implies. One is that you're always guaranteed, no matter how big your sample size is, if you are able to count all your samples, and remember, in a lot of cases we can't. That's why we use samples rather than a population, because we might not be able to get to all Triton students or all the people in the world. So what we do is we modify our equation just to look at the sample size. But the law of large numbers gives us a way that we could do some predictions on our sets. For example, I'll just use a small one here. Let's just say our population is 10. So we have 10 students, and the population here is going to be the students in this class, and there's 10 of us right now. So let's just say that the mean age of all the 10 people, right, the population mean is 20. Right? 20 years old. and I start going to each person individually. How old are you? How old are you? How old are you? So let's just say, I'm trying to make this kind of simple. The first 9 people say I'm 19 years old. Okay? Now, the law of large numbers tells us that our population mean is known. Well, you have to know our population mean for the law of large numbers. The population mean is 20, right? 20 years old. 20 years old. So if I have 9 out of 10 observations that are 19 years old, what would the 10th observation be? In general terms. Just forget all this math gobbledygook. Think about that. If I have a population of 10 people, and the mean age is 20 years old, I ask the first 9 people, how old are you? And each of them say they're 19. What can you tell me about that 10th person? Think about it. You probably should say, well, if the population mean is 20 and the first 9 people you asked are 19, that 10th person has to be older than 20 and probably a lot older than 20. That is the concept of the law of large numbers. Now, of course, it's more complicated than that. Maybe not more complicated, but it gives us more than that. I'm just trying to distill it down to the lowest common denominator. Pardon the pun. See what I did there? Lowest common denominator, get it? Never mind. Anyway, so what we're going to be doing is in this session here, or in this unit, we're going to be going over some of the properties of large sets of data. And one of the laws that we're going to be doing is, as I mentioned, is the law of large numbers. And we're going to have a little bit more detail on it and then discuss some more properties about the law of large numbers and how we could use the law of large numbers for prediction. Now, think about the example I gave you before. If we have 10 people in our class and the mean age is 20 years old, and I ask the first 9 people, how old are you, right? And they say, Professor Hendry, we're 19. Let's just say it's a coincidence they're all 19. And I would ask you, I would say, predict. Predict for me the age of the person, of the 10th person. You might say, well, knowing what you know now, you'd say, well, I don't know, I can't predict the age, but let me ask you the question. What's the probability that that person is under the age of 20? You should know this. The probability is 0. There's no way that that 10th person can be under the age of 20. Why? Because we know that our population mean is 20. The first 9 people are 19. So I would say my prediction would be that the 10th person is going to be much older than 20. And that would be correct. So what we're going to do is I'm going to show you mathematically how you can model that. Now that's important. What are the implications, and the practical applications of the law of large numbers? The law of large numbers are used in statistics a lot. They're used in medicine. They're used in medical research when you're maybe doing drug trials and you have large populations and you're doing samples and you can do a descriptive model of what your data sets are, or a descriptive model of each specific observation that you made, and then build predictions on that. It's used in insurance. You can take a descriptive model of the driving habits of people and their propensity to get new accidents, and you can make predictions based on something like the law of large numbers and other laws too. I'm just trying to give you some examples of predictive math. You could do that in, for example, the Center of Disease Control does a lot of predictive math when it tries to determine, where do we spray for bugs, because we could look at past outbreaks of malaria and figure out where we need to spray for bugs or things like that. Or, for example, in finance, this is used a lot in finance, where, as a matter of fact, there are entire books and there are entire subdisciplines of mathematics that are just dedicated to this, where you could look at the past history of different either equities or bonds, or pick something. And you could take, tens, dozens, hundreds, thousands of data points, and then you could build a descriptive model on that, and then build a predictive model. And then also with that predictive model, you can put in something what's called confidence. Now, confidence is a mathematical term. All that means in English is, going back to our example, we have 10 kids or students in class, and we know that the mean age is 20. And if we ask the first 9, and they say, Professor Hendry, I'm 19 years old. Okay, I can ask you a question then. I would say, give me your confidence level that the 10th person is going to be under the age of 20. You could say 100% confidence that 10th person is not under the age of 20. Why? And we could go over proofs, how the law of large numbers can prove it. Or to expand that example, I could say, what are the odds? I hate to say that word, but what's the probability of the next person, that you ask being over the age of 21? And you could be able to model that. And you could say, well, based on the law of large numbers, we give you 100% probability that person is going to be over the age of 21. So basically the law of large numbers and other laws like the law of large numbers give us a basis to perform mathematical proofs on very, very large data sets. For example, let's just say that you worked for, I'll pick on Geico Insurance. Great company, Geico. Let's just say you worked for Geico Insurance and you were like an actuary, and what your job was to determine insurance rates. Okay, believe me, these are not guesstimates for insurance rates. There are actuaries that use math just like this to determine things like that. So let's just say you're working for Geico and someone asked you the potential of the percentage. Make a prediction on Bob. Bob is 39 years old. Hey, it can happen. Bob is 39 years old. He's in good health. He has a good driving record, nothing but parking tickets. He lives in the city of Chicago. And I don't want to invite bad luck, so I'm going to do something simple. What are the odds that Bob has a meteorite fall in his car? I'm trying to be silly on purpose. You'd be able to model that. I mean, based on the data, you would be able to model that, and you could say there is a 1.5 in a million chance that Bob's car will be hit by a meteorite. And okay, fine. So you could build your insurance rate based on that. But here's the thing: you're going to have someone that you work for that's going to say, okay, Mr. and Mrs. Smarty Pants, you said there's a 1 in a million chance or a 1.5 in a million chance that a meteorite hits Bob's car. Show me the math of how you got there. What is your confidence of this? The law of large numbers and other laws like that give us the mathematical foundation to actually look at descriptive models and build predictive models scientifically and mathematically, where you can walk into that boardroom and say, here are my numbers, here's why I came up with this, and then there it is. Anyway, fascinating stuff, at least if you're me. Just to point this out, predictive modeling is part of discrete mathematics, but it's also its own discipline. So just remember, as you're going through the course that you're in now, that when we go, or if you decide you're going to go into predictive analytics, there's a whole new dozens of doors that are going to be opened for you to explore that. It's much greater than I can describe in a video or even a series of videos. I mean, there are entire courses that you could take on predictive modeling, especially if you're a math major or a finance major. You're going to do this a lot. Anyway, that's all I had for you today. So thank you for making it this far. I bid you all a very well rest of the day. Thank you.